Hey there, engineers! Today I'm breaking down the Joule-Thomson or JT valve. This tiny component packs a punch in air separation units, chilling air to super low temperatures. Intrigued? Let's dive in. First, the JT valve is a throttling valve. As air passes through, it drops in pressure, which in turn drops its temperature, thanks to the Joule-Thomson effect. Basically, when a gas expands through a valve, it cools down. Pretty cool, right? Now let's get into the nitty-gritty. The performance of a JT valve can be boiled down to a few equations. The Joule-Thomson Coefficient, mu, shows us how temperature changes with pressure at constant enthalpy. It's written as mu equals T over pH. Next up, enthalpy H, which stays constant during the throttling process. It's the sum of internal energy, U, plus the product of pressure, P, and volume, V. So H equals U plus PV, and don't forget the trusty ideal gas equation, PV equals nRT, where N is the number of moles, R is the gas constant, and T is the temperature. Alright, time for the fun part. Let's see how this works with an example. Imagine an air separation unit with a JT valve. The inlet pressure is 50 bars and the inlet temperature is 20 degrees Celsius. After passing through the valve, the outlet pressure drops to 1 bar. The Joule-Thomson coefficient here is 0.15 kbar. So, using our equations, the temperature change dt equals mu times dp. That's 0.15 kbar times 50 bars minus 1 bar, which equals minus 7.35 K. This means the air temperature drops from 20 degrees Celsius to 12.65 degrees Celsius. See how effective that little valve is? From 20 degrees Celsius down to 12.65 degrees Celsius. That's the power of the JT valve in action. I hope this gives you a clear understanding of how JT valves work. Stay curious and keep engineering awesome things. Catch you next time.